that now. All right, so if there's no other questions, let's jump into today's week 17 day one material. So we're going to start off from the code base that we set up yesterday, or that we set up on Saturday, where you guys created your first binary learning model. So I'm just going to go through from the top, just to make sure that we're all covering our bases and answer any questions that you guys may have or clarifications. And then we will get to today's material of training the model and creating some data sets for it. So these are going to be our primary library imports. But it's always a good idea to never import libraries willy-nilly. You should know what we're importing. So, Sean, can you tell me what we use pandas for?
Yeah, we've only used it once in the past and during this course. I think it was a way for us to kind of work with a database, right?
Yep, that's pretty
Like to
accurate.
like read, like we used it for this to read the CSV file,
Yep. So
basically.
Pandas is a library that's great for file import and export or reading CSVs and Excel sheets and things like that. It's also very helpful for storing and processing very large volumes of data, like our CSVs. Let's see. Jonathan, can you tell me a little bit about what sklearn, why we use sklearn, or what it does, broadly speaking, in this instance?
I honestly do not have an answer for you.
Okay, that's all right. Anyone else?
Is that what we use to split the data into um, test and train data?
Yes, perfect. So for right now, for our purposes, sklearn is something that we can use to help us prepare the data before we send it to the machine learning model. It has a ton of other tools that we will not talk about, but basically think of it as being used to help you prep your data. And then lastly, this one should be relatively easy. What is the torch library for?
For your
If
tensors?
that's one of them. But more broadly speaking, one of the modules in Torch is named NN. What might that stand for in our context? It's something that we already talked about earlier.
Neural networks.
Neural network, exactly. So PyTorch is going to be the main library that we use to build, train, test, and eventually run our machine learning model or our neural network on stuff. All right, good. So we've got those imports out of the way. So we already talked about how pandas is used to read data very easily. Absolutely fantastic library. I use it a ton. If you enjoy data science or are interested in working with large data sets in the future, highly, highly recommend learning pandas. It's an extremely capable software suite. The documentation and tutorials that are on the web for it are fantastic. You can also use pandas to integrate with your SQL databases and SQL, Excel, JSON, CSVs. It can read and write to a lot of things. So highly recommend taking the time to look into it and learn about its features if that's something you're interested in. So once we take in the data, one thing to always know is data can be flawed. Some data sets will be extremely terrible. They might have a bunch of commas in the wrong places. They might have weird ASCII code. They might have bad characters. They might have missing values. And all of those things can throw hijinks into your data processing. Sort of like when you're importing data from a API. You always want to make sure that you are verifying and validating your data and making sure it's in the correct format before you start using it. That's exactly what we do down here with this replace missing values. Now, we've already checked over the data set on our own before. We've looked at it and examined it, played around with rows and columns, and here I've got a print command to view all the data. So I'm not going to go through and check every single aspect of it, but in general, if this is a brand new data set to you that you've never used before, highly recommend just going through, stepping through your data, going through every row, every column that you end up using, and just making sure, is this data sound or is there something up with it that I need to fix? So once we do that, we need to select features and a target. Can someone talk to me about what a target and what features are? Just again, broadly speaking, for our context.
Aren't features kind of the variables you're looking for, categories, sort of?
Okay, and then what's the target in that case?
Probably what you want it to end up. What, like again, if you're doing A's and B's, the target would be the A. Oh, I don't know.
Yeah,
don't
no,
know.
that's correct. That's correct. So the features are basically the things, think of the features like the inputs and the target like the eventual output. So, for example, if I tell you that my laptop is 13 inches wide, is a touchscreen, it has a Windows button, and it has like 4 hours of battery life. Those are all features of my laptop. The target is whether my laptop is a Windows or a Mac. And in this case, it's a Windows laptop. So by analyzing the features, you can determine the target. That, broadly speaking, is what our machine learning model is going to do. It's going to take in a list of features, you'll train it to take in a list of features and generate the probability that it matches a target. So though again, this is sort of standard nomenclature, just like labels and trait and validation. Again, good terms to know in the machine learning world. So once we've selected our features, in this case, we're using all of the columns of the data except potability, which is our target. However, you don't have to use every single feature or every single variable in your data set. Even if I believe this data set has, well, actually, let's take a look. On the top row, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So minus potability, we have 9 different features. You can very easily restrict it to just being 2 or 3 features if you want to. However, in general, if you have more features and more data, the machine learning model can draw more connections between things, and it has the ability to affect your predictions. I'll keep that in mind. So once we select and standardize our features, we then get to splitting the data. And this is related to, I believe it was Danielle who mentioned that that's what we use sklearn for. And that's correct. So could someone tell me why we need to split the data? Why do our training and testing data need to be different? Why can't I just use the same things for both?
The training sets used to train, no, used to evaluate the model's performance, right?
So the training set is used to train. You were right about that part. But why does it need to be different from the test data?
The,
Oh, go ahead.
well, the testing's used to evaluate the performance. So it tests how well it trains.
Exactly. Yes. So you can think about it again, sort of going back to my favorite example of the times tables. If I tell you that 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4, you now know that information. So if let's say I go back and I tell you, all right, what's 1 times 2? You'll automatically tell me the answer is 2 because I just told you it was. However, if instead I ask you, all right, what's 2 times 2? Now, 2 times 2 is something that you do not know. Automatically, or as in, 2 times 2 is something that I haven't told you directly, but you should be able to tell me that it's 4. So if you tell me 2 times 2 is 3, then I can tell you, nope, you're wrong. You need to go back and relearn the material. If you tell me 2 times 2 is 4, then the model testing was successful. So that's the main reason that we have to differentiate between training and testing data is exactly that. If I test the model on the exact same data I trained it on, it's going to give me an artificially higher rate of accuracy or success than if I train it and if I test it on different data. However, as I mentioned prior to the recording, you want to make sure that both your training and testing data is labeled accurately, which is something that Kim hinted at as well. Because again, if the data is not labeled, then you don't learn from it because there's no part of that that becomes a feedback loop. So, all right, that's training and testing. Let's see. We'll now talk a little bit about PyTorch tensors. Can someone just really quickly explain roughly what a tensor is before we go further in? Anyone remember this from last Tuesday?
Um, the tensor, it's the object that we create because the model has that. It's what we pass into the model.
Yep, that's correct. So it is what we pass into the model. But broadly speaking,
It's the data that we pass into the model. So it's the all the data that we wanted to evaluate. That tensor object has it. Now, I don't know the exact name for why it's called that, but I know it stores the data that we wanted to give to the model.
yeah, no, that's completely accurate. If we want to get a little bit mathematical or technical, tensor is a collection of, it's basically a collection of matrices or vectors that store data to be forwarded to the model. Basically, it's sort of like a bunch of nested lists, broadly speaking, for our purposes. So, we want to convert the data to tensors because tensors just work better for machine learning than using arrays and lists because tensors have directionality and magnitude and different things like that. We will not be talking about the math of the machine learning very much here, but if that's something of interest to you, the 3 blue, 1 brown videos that Jordan linked and that I will completely second. They are a fantastic resource for those of you who are interested in this. Those go into a lot more depth about what tensors are, what sort of algorithms you can run on them with things like gradient descent. Fantastic resource. Please check those out. All right, so once we convert our data to PyTorch tensors, we then do a little bit of a detour to creating our model. So is there anyone who would like to break down this model for me? Um, what are the main things that I want to ask about is what is happening in this init function and what is the forward function?
I know what the forward is,
Okay, why don't we want to tell us?
which I think is cool. So the thing about this class way, it's different from the sequential way. The sequential model followed a strict linear type of process, but within this class, the forward is in a sense the map. We can have it we get to define the path however it needs to go for its evaluation. Um, and so in the init, we are defining the layers, and the sigmoid, of course, is what produces the final output, right?
Yep.
And so we're we instantiate and we inherit from the binary model. And so yeah. That is, this one seems more like how the AI brain would be developed per se. On a low scale. I know there's more to it, but just that forward part, defining how it can all intersect and we get to decide the path that it goes. That's some heavy stuff. Very heavy.
Indeed. Indeed it is. But yeah, that's a pretty good example of forwarding. So thank you for sharing that. But yeah, so the forward basically tells you how the different layers are connected. Now, the real part of my question was, where are the different layers? And how do you know what each layer is? Which is where you can see those in the init. So the first thing to note, again, is that our model is a binary model. It says it right up front. And it has a series of 4 different layers. Now, let's break down each layer in turn. And for that, I'm going to split screen, or try to split screen these. We'll go up to here and just take a look at the top. So if we go up in our code, remember that we have the number of features we have is the total number of columns in our data minus 1, because we're dropping potability. Then it's 1, 2, 3, 4, 5, 6, 7. We have 9 features in our data. So the first layer of our model is a linear layer that's going to take in 9 features because, well, that's how many features are in our data. But then this model is going to then break those 9 features down and turn them from 9 features to a list of 7. So it's going to take all of these different conditions and squish them into basically a summary in 7 variables instead of 9. It's going to pass that information on to the second layer. So the 7 variables created by linear 1, those are going to get sent to linear 2. And linear 2 is going to take those 7, it's going to do its little math, and then it's going to turn those 7 into 4. And then it's going to send those 4 variables that it's created now down to linear 3. And linear 3 is going to take those 4 layers, play around with them a little bit, and then come out with 1 layer at the end. And then that 1 layer at the end is going to get sent to the sigmoid, and then you have your output. So you're starting off with 9 features, which are all of these. You go from 9 to 7, from 7 to 4, from 4 to 1, from 1 to 1, because the sigmoid doesn't add any features. And then you have your prediction at the end. So what I like to do when making machine learning models is I will sometimes physically draw out the number of layers and the number of nodes. So something you can do is draw out like a vertical line and draw 9 little circles on it. And then draw a second line that has 7 little circles on it. And then another line that has 4 little circles on it. And then another line that has 1 circle. And each of those lines, in this case, sort of represents a layer of your model, where you're going from a bigger number of features down to a smaller one, down to a smaller one, and so on and so forth. So again, in our model, we have those 2 components. You have the layers, which is, again, in the init, and then in the forward section, you have the relationship between the layers. So, again, the way that we can create an instance of our model is just by instantiating the class, just something that you all know and love. And then lastly, we can run the model on a given tensor. So let me see if I can run this. Actually, let me just run everything. I haven't run this stuff in a while. That cells ran. These all ran. Perfect. Yep. And then down here, we see that each of these, for example, it says that for even though the label of the first training thing should be 0, because our model hasn't been trained on anything, it's giving us the random value that this is a 0.413 blah blah blah. Likewise, training data set number 406 should be labeled as 1. But because our model doesn't know any better, it's labeling it as 0.3684. So again, the binary classification model will return something to you between a 0 and a 1. So now that we have successfully set up our data, we've set up our training and testing sets, and we have now set up our model, it's time to actually start using this thing. So we can start thinking about how to train our model to let it actually learn based on everything we've set up. Before we keep moving forward, are there any questions about model setup, splitting the data, or any of the Python packages that we've talked about before we get into actually training it?
I have a question about when you were discussing the features.
Mhm.
Will you open back up the the other window? Yes, 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 yes. And can you have them side by side? The code and the yes.
Yeah.
So when it's going through these layers, right? So it's going
Yep.
from 7 to 4 to 1, right? How like is it removing because in a sense these are columns, right?
Mhm.
So it's reducing, but how does it know which of the columns it needs? Because to me, this looks like I am taking away something,
Right.
right?
So it's not dropping columns per
Uh,
se. Like it's not saying I'm going to take in all 9 of these and then I'm going to forget that pH and hardness exists. So now I have 7. And then I'm going to forget the next 3. So now we're only left with 4. It's not doing that. Instead, it is combining the data and analyzing features of it so that even though here we have 9 columns, it's going to represent that data using 7 columns on its own. So the features that come out in that 7 or 4, those are not actual columns of your data. They are how your neural network is interpreting and summarizing your data, if that makes sense.
wait a minute, wait a minute. Will you say it one more time?
So it's not when you're going from a large number of features to a smaller one in a layer, you are not dropping columns of your data. Instead, you are summarizing them in new columns. So the columns, like the 7 features at the end that linear model 1 spits out, those are not these columns. Those are like the machine learning model's own custom columns that are jumbled together all of these in different ways, if that makes sense. So don't worry about dropping data. If does that help?
Yes. So okay. So it's yeah. So ah, that's where the hidden part comes in. Okay. Okay. So then that's where we get to define the weights of what's more important
Right.
regarding the features that we are passing. Got it. Okay.
And that's where the machine learning model learns how to do that on its own. That's where the learning part comes in. Any other questions before we get to actually training the model so that we can actually try to use it? Okay, awesome. So let's get to writing some code. So the first thing that we want to do is we're going to take a look at our PyTorch tensors. So we have our four tensors. We have our X and Y values for training and testing. The X values are all of your inputs, all of your features. The Y values are the targets. So let's say the X value contains the pH, the hardness, the solidity, the other things. And the Y value says, is it drinkable or is it not? 0 or 1. So we need to find a way to take each of these individual training and testing tensors and combine them into a training and testing data set. Now, thankfully, we have some functions that let us do this automatically. The first one is going to be the tensor dataset function. And that comes in from, let me go ahead and import it. We're going to say from torch.utils.data. We're going to import the tensor dataset and the data loader. Now I'll get to what those are in relatively shortly. But those will basically combine your training and testing data together and shuffle them around a little bit. So we'll go back down here and we now have our tensors. So once we have made our tensors, again, we want to take these and instead of keeping the X and Y separate, we want to now squish them together. So we'll now create combined testing data set and combined, see, this is going to be training data set and combined testing data set. So the training data set is going to be a tensor data set consisting of the X training tensor and the Y training tensor. Because again, we want the testing, all the training data to be in one place. And we can do the exact same thing for the testing data set. So I'll say the testing data set is going to be another tensor data set of the testing tensor and the Y testing tensor. So this way, if I give you the training and testing data sets, before the training data was unlabeled, they would not, this X train on its own would not tell you if the thing that you're analyzing is potable or not. But now we've combined them using our tensor data set, our training data is now labeled with the appropriate target. You know, for a given row in this tensor data set, you now know if you're based on all of the features, what the correct answer should be. It's kind of like we're creating an answer key. So once we've created our data sets that now have the answers built in them, we now need to combine those with a data loader. So what's the best way to explain this? A data loader is a way that is something that kind of shuffles your training data so that you don't think that the training data is in a pattern. Think about it sort of like you're studying flashcards. If I give you a set of 20 flashcards and I tell you to memorize them, then I give you the set of 20 flashcards again in the exact same order, you're going to learn to anticipate what card comes next, which makes it easier for you to memorize the information. However, that doesn't tell me if you've actually learned the material. So the way to tell if you've learned the material is to shuffle the flashcards every time I give it to you, right? That's something that's sort of like softwares like Quizlet do, or if you're quizzing or if someone's quizzing you, they'll change the order of the questions. That's exactly what a data loader does. So we're now going to create, so the data loader will shuffle the order of the training and testing data every time they are called. So every time the model is trained or tested, it'll be trained on the same data, but in a different order than it was before. So let's just set up the training data loader. We'll do that by just saying data loader, and we're going to take in the training data set. The next thing we'll want to do is we'll want to set a batch size for basically, do we want to shuffle the order of everything, or do we want, which is going to take ages for giant data sets, or do we want to shuffle them in chunks? And ideally, you always want to shuffle things in chunks or batches. We'll set it to 32 here. Usually people like to set their batch sizes to multiples of 10 or powers of 2, like 2, 4, 8, 16, 32, 64, da da da, or like 10, 20, 50, 100, 500, and so on. You don't want your batches to be too small, but you also don't want them to be massive. It depends on the size of the data set. So in our case, how large is this data set? This data set has about 32 or 3,300 rows. So if we're splitting this into batches of 32, and again, assuming that we're testing on the whole, training on the whole thing, which we aren't, we're training on about 80% of it, but just for assumptions, then you'll have 100 batches that you can shuffle around the orders of. So like 100 cards. You have a lot of different ways you can order that. So about that much is probably good. If we had a batch size of 300, then you would only be shuffling 10 chunks, which is, less effective. You don't have as good a shuffle. So giving a relatively small batch size that allows you to shuffle things quickly is important. So the last thing we need to do, of course, is tell the data loader that we do actually want to shuffle this data. And we're going to do the exact same thing to set up a testing loader. And we'll just change the data set to be the testing data set. But for right now, we're not going to shuffle the testing data set because we aren't going to be talking about testing today. However, as we do start getting into talking about testing, improving the model training, verification, you may want to shuffle or change your test data eventually. But right now, the only thing we want to talk about is creating those data loaders. Okay, so the next thing that we can talk about now is actually starting to train our data set based on the data that we have. So we have a couple of main components to training a model. You never train a model just one time, because if you train it once, it doesn't have the opportunity to learn from its past mistakes. So let me actually add a markdown cell. So training process. So the first thing that you want to do is run the model on your data, obtain the model's prediction based on the data. Then you want to calculate the loss, aka difference between predicted and actual values. And again, we're given the actual values in our training data. And then we want to update the model parameters, which I think Mike touched on this earlier, but those are going to be things like the weights and biases. I'm going to update those parameters in order to minimize the losses, which leads to hopefully increased accuracy of our predictions later on. And then we want to repeat this process n times, where n is the number of epochs. One training process, or one training process is called an epoch. Mike, did you have a question?
Yes.
Go for it.
You just said that we should not limit the training of the model to one time.
Yes.
I'm curious. I mean, not to do a deep dive, but this is something that is electronic, right? If we already gave it the labeled data or how it needs to know something, right? And it saves that information. Why would it need to be retrained over and over and up until we say, okay, now you have learned this, if you've already got the labeled set of instructions, right? If I tell you 1 + 1 is 2, well, you just learned it. Even if I give you 5 + 5, I mean, once I give you that test, right? I don't.
So if I tell you that 1 + 1 is 2, 1 + 2 is 3, 1 + 3 is 4, and I give you like 300 times table or 300, addition formulas. I cannot expect that you will memorize all of those on the first try, especially because just like a human, a neural network memorizes things based on pattern recognition, right? It takes in all this information and it tries to crystallize it down to simple pathways. It's the exact same thing with training. I can't give you 300 times tables and expect you to memorize all of them perfectly. I need you to practice them, and then after you practice them, I can correct you. And then once I correct you, then you change your behavior, and then we try it again. So if I just train you, give you the data once, and I say, all right, you have the data, go, you're good now. Your accuracy is going to be absolutely terrible because you're not learning from your mistakes. It's the exact same thing with training a neural network. You have to give it more than one opportunity to modify its behavior so that it can learn from its losses. Does that make sense?
Yes, it that makes sense what you're saying. And I don't want to go off into too much theory, but it just, to me, this gets deep because we're dealing with something that is electrical, right? A state of 0 or 1, and it's storing data and this and that, but now there's another layer that says, oh, we are teaching it now and training it,
Mhm.
but it's still a program. But yeah, I just that's interesting.
For sure. But yeah, anyone else have questions about the broad process of how we train a model before we start actually coding the training process? Or any conceptual questions I can answer? Yeah, this stuff is weird. Coming from writing an algorithm that, runs on for loops and if statements, and you can trace through the code and figure out, yes, given this input, it should output exactly that, to, all right, I am creating a bunch of stuff, I'm sending it into a black box, and it hopefully is going to give me the right answer. No, they are not fundamentally different, but they need to be machine learning models and normal functions need to be thought of in different ways. So, is there anything I can clarify before we keep moving on? Okay, so let's get to talking a little bit about training. So, again, the first thing that we want to do is repeat the training process multiple times. How many times do we want to repeat it? That's a variable that we set and that we can change. So let's call it the number of epochs. Because again, one training process is called an epoch. The number of times we run it is going to be the number of epochs. Well, let's say that we're going to run it 20 different times. So now we want to repeat this process. So we might as well just say for epoch in range num of epochs. So again, this will runs the code inside the loop num of epochs times. And then now we can effectively train the model on the training data. The way that we can do that is getting our output initially for each combination of features and labels. So let's go back to that training loader, right? So the training loader this will essentially be a nested collection of features and associated labels, right? So in simple English, this is the training loader is basically each row of this data. So the features are all of these numbers that we're providing as inputs. The label is 0 or 1. So naturally, when we are training our model, we want to evaluate our model on every single row of our training data. So to do that, we can say for, and then features and labels in the training loader. Then we can train, so training model on the training data on, let's say, all of the training data. And then now we can, firstly, we can evaluate the model on the features. So get the result of the model. And let me write that separately. Obtain model prediction, which is that first step that we talk about here. Obtain the model's prediction based on the data. Then once we've obtained the model's prediction, we need to compare model prediction to the actual value, which is the label. Then we can compute the loss. And lastly, we can tell the model to modify its behavior based on the losses. This step here is known as optimization. There we go. So roughly speaking, this is going to be the rough scheme of training that we're going to follow. So the first thing we want to do again is we want to evaluate the model on the features. So if I give you a bunch of data, if I give you a times table, I want you to tell me what you think the answer is. So the way that we can do that, just like we did up here, where we're running the model on the first item in our training tensor, we can obtain the model's prediction by just saying, I'll just say here, model prediction equals model on those features. Because remember, the model can only predicts data based on what you give it. In this case, we're giving it our training data. All right, so we've come up with our prediction. Now we need to compare the model prediction to the actual value and compute the loss. In order to do that, we are going to end up using a loss function. So the loss function, well, it basically, there's really not much else to it. It can be used to compute the loss that we're going to calculate. So the loss is going to be based on some criterion, which we'll get to in a second. And that basically takes the prediction and it's going to take your labels, but not all of the labels. It's going to take one specific label, which is going to be located here. And it's going to take that as a float, as labels are integers. Now, before we keep going, let me take some time to summarize. Oh, and my computer is glitching out. Hang on one second. Okay, there we go. So, to summarize a little bit of what the loss function and the criterion does. So, the criterion is used in order for us to calculate the loss and also optimize and adjust the weights and the weights and biases based on how bad the loss is. So if, for example, you adjust the weight, you run the model and the weight and the loss is very low, you're probably pretty good because your expected result matches up with what the result you got is. So you don't need to change the weights and biases too much. However, if there's a huge difference between the biases and or between the expected and output values, then you know something's wrong with your training. So you need to go ahead and revise your weights and losses. The thing that can tell us that is known as a criterion. So, and the criterion is basically a loss function. So in our case, because we are using a binary classification model, our criterion is going to be the BCE loss function, which is binary classification loss function. We will get into what this means a little bit more tomorrow, when you talk about how to improve your training. But for right now, the main thing that we need to know about the loss function is it tells you the difference between your model's prediction to the actual value that you're expecting. The bigger your loss is, the worse you're doing when you're training. So again, now we've computed the loss. So the next thing we need to do is we need to, oops. Here, let me clear that output for now. And we'll get to why that happened in just a second. So now that we've created our loss function that tells us how off the mark we are, we need to go back and tell the model, hey, you need to get your house in order. Here's how badly you messed up. And we do that by using something called backwards propagation. So the model that we use has two steps. The first one, if we go back to, let me see if I can find a picture. Yeah, I guess we can use this slide as an example. So there's two parts to the machine learning model process. The first one is going to be the forward step. The forward step is where you send the model, you send the data from the input through all the features, it does its little magic, and it gives us an output. The backward step is where we sort of, outside of the model, we retroactively analyze and we say, how bad is the output compared to the input? And what things in the model do I need to change or optimize? And that is what we're going to do now. So let me flip back to VS Code. So the first thing we want to do is that backward propagation step, which again is where we calculate the loss with respect to each parameter of our model. And then lastly, we need to optimize the model. So we can now run optimizer, change weights, biases, etc. So we need to now actually design or say what type of optimizer we're going to use. So in this case, we're going to use, believe it's the Atom optimizer, which uses something called gradient descent. I'm not going to go into the explanation of that right now because I don't know if anyone wants to see multivariate calculus at 7:30 in the evening. If you do and are like me, the 3 blue, 1 brown videos have some wonderful visualizations of how gradient descent works, and I can't recommend them enough. But basically, the optimizer is going to pull some fancy math tricks in order to determine where your loss is the lowest and how the model can get closer to achieving a lower rate of loss. So the Atom optimizer is one such optimizer that we can use for this purpose. Again, I believe we'll talk more about optimization tomorrow. This is just meant to be an introduction to that. So we'll set up the Atom optimizer, and we'll take in the model's parameters, and we're also going to lastly specify our learning rate of 0.01. So there's the learning rate will tell you, and roughly speaking, the amount of change in the model's parameters, where again the parameters equals weights and biases. So if you have a small learning rate, then things are not going, your model's not going to learn very quickly. If you have a high learning rate, then your parameters are going to be changing all over the place, which might enable you to get a higher rate of accuracy more quickly. But right now, because this was what was written in the example, we'll leave the learning rate at 0.01. But again, we are computing the loss. We are calculating the loss with respect to each parameter, where again, a parameter is going to be a weight and or a bias. And now the last thing that we're going to do is we are going to run our optimizer. So we're going to tell the optimizer to optimize itself based on, or optimize the model based on whatever has happened. We also, initially, we need to basically going to say that we're going to reset our optimizer. So we're going to say optimizer dot zero grad, which will again, for the gradient descent, this will set the gradient that we're evaluating to 0, not to go too far down the mathematical rabbit hole. But that's kind of just like resetting it for our purposes. So I'm going to pause for a second. Do we have any questions about any of the stuff I've done in here so far?
I have a question.
Go for it, Mike.
All right. For the optimizer,
Mhm.
we're saying that we can adjust as far as if it learns slowly or if it learns faster.
Yes.
And so I'm curious how that has an impact on memory usage because I'm thinking and I might be heading in the wrong direction, but because these are values being set, if we're saying learn from a little bit, well, I'm thinking that's like a small amount of whatever it uses behind the scene to know how to learn. I'm thinking that's just using a little bit of stuff versus if we say I want you to learn faster, is that taking up more memory or I don't.
I don't believe so. The main thing that's going to impact your memory usage is how much training and testing data you have. The only thing that the optimizer is changing, again, are those weights and biases, which are numbers attached to your nodes in your layers. So it's just changing the parameters associated with each of these layers. It's not changing your data itself. So I
Okay.
don't think that should have any impact on memory,
Okay.
but I would recommend double checking.
Okay. Okay. Thank you.
Any other questions about what's involved in the training process or how we turned this into the pieces of code that you see below? All right, there's one last thing that I like to do, which is at the end of every training run, aka after you've gone through all the training data, it's always a good idea to keep track of the loss. Basically, as you train the data, or as you train your model more times, your loss should go down. Sometimes your losses will go up, and that happens if you're overtraining the model, which we will talk about tomorrow. But basically, you want to make sure that as you're teaching the model, it gets better at what it's supposed to do. If it's staying the same or gets worse, you don't need to spend as much time or memory training it, training it, training it. You can relax a little bit. So I just like adding in a little print statement that just states what the epoch is. So we'll just say epoch plus 1 because we're starting at 0 out of num of epochs. And then we'll just say that the loss is going to be the loss dot item. And oh, there we go. Okay, cool. So let me try rerunning all of the code from the top. So clear all outputs, and let's see what happens. So we have our tensors. We now scroll down here and we see our model is being trained. So there's a couple. So for again, the model has now undergone some training. Now we can see that the losses started at about 63%. Not great. Then it dipped down to around 50 or 60. Then it went up, then it goes back down, then it goes up. But the losses are not really changing much. They're kind of fluctuating in this 60% to 70% band. That's not great in terms of training losses. In order to change that, we can up the learning rate. So let's say we change it to 0.1. Right, so I'm gonna just rerun this model, and now we'll retrain it, and let's see if anything ends up changing. Now we see here, if I've upped the learning rate to 0.1, the initial loss starts out pretty high, around 70.71. But unlike before, we now see that it's kind of steadily going down, right? So it sort of bottoms out here around like the 0.58, 0.6 mark, and then it goes back up again. So that's a sign that we are overtraining the model because the losses are going back up in training. However, no, that just goes to show that changing the learning rate of your model does make a difference on your training accuracy. However, there is a difference between training accuracy and testing accuracy. Because training accuracy is how you're checking, basically, how well is it learning the material. The testing accuracy is how well does the model apply to data that it's never seen before. So that's the last piece of code that we're going to write for tonight. We're going to be testing the model. So the first thing that we need to do is we're going to import a package called Torch Metrics. So if you haven't already, and if you're following along, make sure that you are pip installing Torch Metrics into your virtual environment. Once you've done that, I'm going to go back up to my installs and my imports, because I like to import everything at the top, because some imports can take like 4 minutes to import things. You do not want to be running an import statement halfway down your code if you could have done it all the way at the start and never have to do it again. So I'm also going to now import from Torch Metrics. Let me move that. From Torch Metrics, I'm going to import the accuracy module, which we can use in order to calculate, well, the accuracy of the model. So let's go back down and let's figure out how this works. So we've imported it. I'm now going to just specify that I am going to write a function called accuracy based on the accuracy model that is going to specifically focus on the accuracy of a binary classification model, which again, we are using a BCE, so task is binary. That makes logical sense. Now that we have done training our model, we now want to turn it from training to testing or evaluation mode. So we're going to now say model.eval and say that we'll just say change model to testing, aka evaluation mode. So that will change certain aspects of the model's behavior regarding taking in and evaluating data. So the last thing that we're going to do is we're now going to write a for loop to go through all the testing data. So we're first going to say with torch.noGrad, which again adjusts properties of the gradient descent, we can now copy some of this code. I'm going to copy over all of it right now, and then we will delete and modify pieces of it as needed. So we are not going to be optimizing anything because we're testing the data. We are not going to be changing anything in our model. We still need to get our model's prediction for the now testing data. We do not need to compute the loss in this way, but we do need to actually compute the model prediction. So change this to be model output exact, and then we'll say that the model prediction is going to be the model output exact dot round, which is basically going to take the 0 point blah 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 that it generates, as we saw up here with those 0.45 or 0.49, it'll turn that into, well, a 0 or a 1. And then lastly, we can update the accuracy of our model to take into account the model prediction versus the labels. So that will compare the output of the model to what the actual 0 or 1 data is. And then now, instead of printing out the epochs, we don't have epochs anymore. We now just have the accuracy. So forget that. We can just say accuracy. And now instead of the loss, we are going to go back to our accuracy object. We're now going to compute it and then take the itemization. So don't worry too much about what compute and item are. I'll send some links to documentation on that. But basically, this component, this piece of code can be used to give you a better way to evaluate the accuracy of your model than just summing up a bunch of things and subtracting things. It actually runs some code on its own in order to do that. So let's go ahead and run this cell. And model accuracy is not defined. That is because I did not run the import statement. Oh. Okay, is this running line by line? It is. That's not what I wanted to do. Let me run the whole cell. Not the debug console. Let's go back to my terminal, please. And let's run the testing cell one more time. So we see here that the accuracy of our model is about 0.268, blah, 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 blah. Now, there's a critical thing to notice. When your loss is different from your accuracy, sometimes your loss may be higher than your accuracy. But the reason for this is, again, loss is applied to your training data. You want to minimize your losses as you're training. Your accuracy is related to your testing data. You want to maximize the accuracy of your model. So minimize losses by using backward propagation and optimization in order to change the weights and biases as you go, and speed up your learning rate if you need to. Evaluate your model by checking its accuracy against your testing data. That's it. That's the 101 on how we train and test machine learning models. Any questions about any of the concepts that we've discussed so far? So whether that be setting up the training process, preparing the data sets and data loaders, writing our functions for training and testing. Any questions on that?